then I'm still paying you. I got the hard ass beats like the crack of the tech. Still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. Still paying you. I'ma make y'all pay for the dues.
All right, let's get started. Round of applause for DJ Cash. Again, take a minute out. So a quick comment. I was going to give you a thank you for being professional this semester. Like my other DJs always had like ex-girlfriend showing up at my office or like behind on child support payments. But you've been very professional. I appreciate you being here always on time. So thank you again for even though the semester's not over. I was just thinking about this morning. Oh man, DJ Cash doesn't have any problems. It's kind of nice. All right. So guys, a lot to get started, a lot to discuss. So let's get started. Again, for you guys in the class, the docket looks like this as we finish up near the end of the semester. Homework 5 is going to be due again this Sunday coming up. Project 4 went out last week. The recitation will be tomorrow, November 18th at 8 p.m. on Zoom, and the link is on Piazza. And again, the write-up is quite exhaustive, deliberately so because transactions are super hard. We're trying to be very thorough on what exactly you need to do for Project 4, so you don't get lost. So please read that before you show up to the recitation. And then the final exam is going to be Thursday, December 11th at 1 p.m. It's a 3-hour exam. I don't know where it's going to be. They haven't scheduled it yet. So please don't make travel plans before this date because there's no makeup and there's no early exams. Any questions about any of these things? Yes? Question, what happened to the advanced class 721? Other people have emailed me about this. Jignesh Patel is the other database professor at CMU in the CS department. They made him the department chair because nobody else wanted to do it, but it's interim department chair. And as such, they were supposed to find a replacement for him so that he could teach the intro class next semester and I could teach the advanced class. They have not found a replacement yet. They haven't even done it. The dean hasn't even started the external search yet. So at this point, there's nobody can teach the class other than me next semester. So I can't teach 721. But do you think they would find a replacement? The question is, do I think we'll find a replacement? Be nice, yes. Do you want to be department chair? No. Or nobody. It's a thankless job. Yeah. So at this point, it's outside of my hands. I don't have the controls. I apologize, but there's nothing I can do at this point. The question is, does he get a raise? Again, that's above my pay scale. I don't know. Right. All I know is he's teaching 721 now and being department chair and trying to do awesome database research with me. So it's not sustainable. So if it gets added back, I will email everyone. But at this point, don't bank on it. The question is, what? I don't know. I mean, ideally, yeah, I can't be 2 weeks into the semester. Oh, guys, want to come back? No, January, early January. But again, don't bank on it. Yeah, I'm not happy. It is what it is. But what can you do? It used to be the intro class was only once per semester because it was just me teaching it, and the wait list was 500 people, right? And so we stole Jignesh from Wisconsin. Maybe we'll hire somebody else, but even then, if we hire somebody else if we hire another data person this year, then that person could potentially teach the intro class in the fall, and then I could teach 721 in the fall. But spring is not looking good. Okay. All right, so moving on. What else we have going on? So we have a lot of cool database talks coming up. Tonight or today, after this class, we'll have Ben, who gave the talk in class before, from Firebolt, talk about how they support Iceberg now. Snowflake is on campus today and tomorrow. One of my former students is giving a talk tomorrow at 12 o'clock. I think the University Recruiter is here as well. I don't know I know they've made some offers to some students for full-time positions. I don't know what the status of internships and full-time offers beyond that from Snowflake. But they're on campus here if you want to meet up and talk to them. And then the following week, we'll have this is a system out of the UK called XTDB. This is a weird one. It's a time series database, but it runs on multiple dimensions of time. We don't really cover time series databases in your class, but just think of I want to keep track of stock ticks when these events occur. And then I also want to keep track of I can have another dimension of time, what would happen if I traded this stock at an earlier point in time. So now you have sort of two parallel dimensions running on. It's wild stuff. This is used not this system, but time series databases are widely used in fintech and trading world. But again, that'll be next week on the Zoom seminar. Okay. All right, so last class was the last lecture we did on concurrency control, and we finished up talking about multi-version concurrency control, and we said this was a mechanism we could allow us to basically make multiple physical versions of a logical object in our database. So instead of overwriting the data directly, we'll make a copy or make an actual physical version that has either the delta of the change or the actual change itself in our system, so that we can do a bunch of tricks of allowing consistent snapshots of the database when we go read things. And we talked about how, like, not just in MPCC, but all of the other concurrency protocols we talked about before, how the design decisions we make in our concurrency protocols are going to affect all throughout all the other parts of the system, because the other parts of the system need to be aware of transactions and what transactions are doing to in the system to make sure we're doing things correctly. So what we talked about so far has given us three of the properties of acids. We got atomicity, consistency, and isolation. Today's class and next class, we're going to talk about how we guarantee durability as well as atomicity after a crash. Okay? So here's the motivation of the problem we're trying to solve here today, or for this week. We have a transaction T1, which is a read on A, write on A, and then commit. Right? So we know how to do reads, right? Ignoring how we find object A, right, in a page on disk, index, whatever, it doesn't matter, right? We know that in order to read this object, we first got to make a copy of the page out on disk in our non-volatile storage, bring that into our buffer pool, hand out the pointer to the execution engine so the operators can access this data. Then now we want to do a write on A. Okay, ignoring multi-versioning, say, I'm doing a single version system. I apply my change directly in my page, in my buffer pool, right? And then I go ahead and commit. Again, the property of commit is that we're telling the outside world that all the changes for your transaction have the ACID guarantees that we care about, right? So we've told the outside world that our transaction is committed. But then the problem is, if there's a bad storm and there's a major disruption to power, ignoring whether we have battery backups or whatever, doesn't matter, right? The system crashes and we lose everything in our buffer pool. And of course, the problem here is that we told the outside world that our transaction committed and we applied their change, but now if we upon recovery, assuming we get power again, when we come back, we're not going to see that modification we made to A because we didn't write it out to disk. So that's the problem we're trying to solve today and next class. How do we make sure that if we tell the outside world your transaction is committed, how to make sure that no matter what happens to our database system, even if the data center melts down, we won't solve that problem this week. That'll be when we talk about distributed database system. But like if the whole thing falls in a giant sinkhole, we can still come back and recover your data. So that's the problem we're trying to solve through crash recovery. And the idea here is that it's the algorithms we're going to implement in our database system so that no matter what happens to our database system, as long as if we tell you that your transaction is committed, then we'll guarantee that we'll retain that data. And we can guarantee the consistency, atomicity properties that we want, despite what happens. Now, just because we store it and say you committed, and even if it is durable, someone, of course, can come along and overwrite your change because the next transaction, but that's okay. That's the normal operations of the database system. It's really like if things crash, how do we come back and not lose anything? So our recovery algorithm is going to have two parts. The first would be what we'll talk about today, and that'll be the things that the data system does during normal operations, during normal execution of transactions and queries, so that it can set itself up to be able to recover any of those changes if there's a later crash. And then next class will be how do we go back after a crash, look at all the things we're going to record today in our data system to go figure out what was going on in the system at the moment of the crash, and how can we reconstruct the state of the database to put us back where we should be. Another important thing to understand when we talk about this as well, going back to my diagram here, ignoring the crash part. But as soon as I tell you that your data is committed, like you say, I want to commit my transaction, as soon as you get back the acknowledgement that the commit was successful, then we should be guaranteed that your data was successfully stored. Now, there may be a race condition where you say you want to commit the transaction, we can make it safe out on disk, but then before we send you the network message saying your transaction is successfully committed, the system crashes before that network message goes out. That's still okay, because it's up for the application to go back and say, okay, did my transaction actually commit or not? People don't write code that way, but that's, in theory, that's what you're supposed to do. All right, so today we're going to first talk about what the kind of failures we're going to have and how we want to manage this in our buffer pool. Because the buffer pool, again, that's where we're staging all the data in memory before we make any changes to them. We need to be aware of what's going to happen when we're allowed to do certain things in our buffer pool. Then we'll talk about the two main approaches to guarantee durability: shadow paging and write-ahead logging. The spoiler is write-ahead logging is what you're going to want to use, and most data systems are going to go ahead and use this. Then we'll talk about different logging schemes and what you can put in your write-ahead log, like what data should actually be. And then we'll finish up talking briefly about checkpoints. And I'll show a sort of naive checkpoint scheme that works in conjunction with the write-ahead log. And then we'll see the problems with it. And then next class, we'll start off with doing better checkpointing. Okay? All right, so at this point in the semester, this should not be a shock when I say this. But again, we've been assuming this assumption of our sort of conceptual database system we've been talking about through all these lectures, where the primary storage location of the data, of the database itself, is going to be on non-volatile storage. An SSD, spinning disk hard drive, S3, it doesn't matter. And then because we can't manipulate that data on non-volatile storage directly, we always got to copy it into our buffer pool, which runs in DRAM, which is going to be volatile storage, right? And it's going to give us faster access. So anytime we want to manipulate data, we got to copy into memory, do whatever changes we want on that data, and then we're going to write that dirty data out the disk at some point. Right? And again, we can't do byte, although once it's in memory, we can do byte addressable modifications. The granularity that we're going to interact with data on non-volatile storage is going to be through pages, 4 kilobytes, 8 kilobytes, or whatever. Right? And then the hardware itself can only ensure that 4 kilobytes be written atomically. So again, the property we need to guarantee or we need to provide in order to say we have a durable transactions is that for any changes that a transaction makes, once we tell somebody the transaction has been successfully committed, then the data has to be durable. And of course, that means we can't have any partial changes that for any transaction that's been committed. We don't want to write, they have the transaction modified 2 pages and only one of them make out the disk. Or if the database page is 8 kilobytes and therefore we got to write 2 4 kilobyte pages out to the hardware, we don't want the first page to be written, but not the second. And if we're telling the outside world that our transaction has successfully committed. So today is about understanding how to make sure that our changes are written out the disk in the right order, so that again, next class when we come back, we make sure that we have what we expect to see and enough information for us to recover the database back to the correct state. So the two mechanisms we need to have are undo and redo. And this should be kind of obvious, but we're setting up to do something more sophisticated. So undo is the mechanism we use to remove the effects of an incomplete or aborted transaction, right? Again, that can happen because either the transaction itself says it wants to abort, called rollback explicitly. The concurrential protocol says you can't commit, and then the transaction gets rolled back. Or again, the transaction is in flight or is active, and then we crash, and we got to make sure we roll things back. Redo with the mechanism that allows us to reapply the changes of a transaction that has committed. So we want to make sure that we reinstall or that we install the changes that they did when they were normally running, so that again, upon recovery, it looks like but it is as if that transaction fully executed or did fully execute. So how we're going to support undo and redo is going to depend on the policies we're going to have in our buffer pool. So let's go back to this example here. Now we have 2 transactions. T1 is going to do read on A, write on A. T2 is going to read on B and write on B. Again, I'm showing all of this, just sort of moving pages back and forth between buffer pool and disk. There's still going to be the concurrency protocols that we talked about before, like 2-phase locking or OCC. All of that's still going to happen above all this as well, but we're ignoring that for today's class because in this example here, they don't conflict, therefore they can write independently. So T1 is going to start, wants to read on A. It's not in our buffer pool, so we know how to go out to disk and get it. We fetch the page. and we store it in our buffer pool. Now we're going to do a write on A, and we'll update A, make A equals 3 there. Now there's a context switch where T2 starts. It does a read on B. That's already in the buffer pool, so that's fine. We can read that page. And then now we're going to do a write on B and set B's value to 8. Now B wants to commit, right? Again, assuming this is one page, right, with three cells or 3 blocks in it. So at this point here, we need to make sure before we tell the application that T2 has successfully committed, its changes have been written out the disk, right? The problem is in the same page as where B is located, there's also A. So the question is, should we allow A's dirty change to be written out the disk as well? Because it's not committed. So let's say we do write it out. Put A equals 3 and B equals 8, and we update that single page out on disk, right? So now we can tell T2, haha, congrats, your transaction has been successfully committed, and they're happy. But now when T1 starts running up again, now they invoke rollback, and now we need to make sure before we proceed any further, we don't have to block on the rollback request. So the application says rollback, we'll immediately come back and say, yep, got it, no problem, right? But now it's our job and the database system to go clean things up. So now we got to make sure that we go remove the effects of T1 in that page because we flushed it out the disk. So what's one way to do that? It's not a trick question. It's kind of obvious, right? Go fetch the page back in, see that it matches what I have now, and undo the effects of T1. Do you think it's a good idea or a bad idea? Is it correct? For one page, yeah. But always think in streams. What if I have a billion pages? Do I really want to go out and bring back in a billion pages, reverse changes, and write them all back out again? No. Because what happens also too, if I crash halfway through that updating a billion things, now I got a bunch of torn writes I got to go clean up. So there can be 2 policies that are affect what the database system is allowed to write out to disk and when is it allowed to write out the pages to disk. The first is going to be called the steal policy. And this determines whether the data system is allowed to evict a dirty object, again, think a page, a dirty object from the buffer pool that's been modified by a transaction that has not committed, and therefore is allowed to overwrite whatever the most recent committed version of that object out in non-volatile storage, or out in our disk. So if steal is enabled, then you're allowed to evict things and overwrite what's out on disk. If no steal is enabled, then you're not allowed to do this. So this all ties back and up to ties together with project 1 now, because now in your replacement policy algorithm, like ARC or LRUK, whatever you're using, it's got to be aware of which of these ones you're actually doing, because it has to then determine if I have a dirty page, am I allowed to write it out or not? And I'll say also too, I'm showing steal, no steal. It's not like you do steal for some transactions, no steal for other transactions. Like your implementation only does one of these. The question is, if it's no steal, then some transactions may never be allowed to finish. Yes, we'll get there in a second. Yes, the thing they point out, which they are correct, that if I am not allowed to write uncommitted pages out the disk, then how would I ever handle a billion updates where I can't everything fit in memory? You can kind of get around that by writing things to the side, but we'll get that in a second. All right, the other policy is called the force policy, and this determines whether the data system is required to flush all the dirty pages from a transaction that are modified by transaction before the transaction is allowed to commit. So when I get that commit message from the application, I don't respond back and say, yes, you've successfully committed, until all the pages that it's modified in the buffer pool have been written out the disk. And if I say no force, then I don't require that. All right? So forcing is going to make it easier for us to do recovery later on, because I don't have to worry about whether a transaction has all its changes made out the disk or not. right? If I'm totally committed, then I got them all out on disk. But I still may have to clean things up to make sure I handle torn transactions. All right, so let's look at an example of no steal and force. Again, no steal means that I'm not allowed to evict dirty pages before a transaction commits. And then force means that when a transaction commits, I have to write all of the changes out the disk. So I start off again. T1 does a read on A. I fetch that page, bring it into memory. Then I do the write on A. I update that single record in the page. Context switches over to T2. T2 does a read on B. That's fine. That's in memory. Does a write on B. That's in memory. We overwrite the existing value. Now I go ahead and commit. And again, under the force policy, before I can tell the application that T2 is successfully committed, I got to write out that page that it modified. But the problem is, in that page, I also have changes from T1 on A, but T1 is not committed. So no steal says I can't write out that page at all. So I have this sort of conflict here that says one transaction says flush everything, the other transaction is not allowed to flush anything. So a simple way to handle this is just make a copy of the page, only include the change from the uncommitted from the transaction that's committing into that new page, and then that gets written out the disk. Yes.
Why can't the changes? You're not stealing any. You're not affecting the page that T1 wrote.
The question is, why is no steal preventing us from writing out that page? Because I can't write pages. I can't write modifications from transactions that have not committed yet. They just have to be in the same page. Yes. The question is, how do I know the original data of the page? We're getting there in a second, but assume your transaction maintains some metadata like the undo redo to know what it changed and what it changed it from. So the question is, what if there's no space to make the copy? Correct, yes. You're poking holes to this, yes. I'm not saying this is a good idea. This is the straw man, so yes. Yes?
It's kind of similar, but I was going to say, is it an option to just wait, like you do T1?
The question is it an option to wait on T1? I mean, wait for T1 wait for T1 to do what? Sorry.
Well, like,
Who's waiting? T2 is waiting for T1?
like in a way, yeah, T2 is waiting for T1.
The question is, so yeah, in this case here, should just T2 yield for T1 and wait till T1 does something that I can decide what to do? Shadow paging will do this, but how long should you wait? What if the person in T1, was typing at the terminal and walks away? So the Databricks talked about this, and they said that people are in like notebooks in Databricks, people start transactions and then they get up and walk away. And then, so they had to set an automatic timeout to kill transactions if they run for 24 hours. Do I want to wait 24, should T2 wait for 24 hours? No. All right, so the advantage of this now, if we do this approach, it's really trivial for us to roll back T1 now, because we just go reverse the change in our page, and none of its changes made it out the disk, right? The no steal prevents that. So we don't have to do any cleanup with no steal, because we know whatever's been out on disk is from transactions that I've committed. So that's good. So I was saying it's a straw man. This is the easiest thing to implement, right? Again, of course, the problem is that you have to have enough memory so that you can maintain the write set in memory, without running at the disk. Assuming you can do that, then this is pretty simple to do, and it makes recovery trivial because again, when you come back on the disk, is going to look exactly the way it should, because it's only going to contain information from committed transactions. That's not entirely true either in the example I'm showing here, because there's no metadata, there's no additional metadata to say that all the changes from a committed transaction have been written out to disk. In my toy example, they're only writing one page, and that can be done. We can assume that that's done atomically. So the way you really implement no steal and force is through a technique we talked about early on called shadow paging. And this is what IBM invented in the 1970s on System R. This is the first way they wanted to implement and support durable transactions in one of the first relational database systems. I don't know what Ingress did in the early days, and Oracle came later, and Oracle didn't do this. So the basic idea is that shadow paging is that you maintain two copies of the database. The master copy is going to contain changes from only committed transactions, and then the shadow copy is sort of temporary space where uncommitted transactions are making changes and can write them out to disk if necessary to swap them out in order to get space. But because they're not overwriting the master copies, then this is okay. So that now if I crash and come back, I just ignore whatever's in the shadow copy database because the master only contains the data from committed transactions. And then to make sure that we know that all of our changes from a committed transactions have been successfully made it out to disk, I'm going to have a single record called the master record, which is basically a pointer that says, here's the latest page table. Here's the current page table of the database system, or sorry, not the page table, directory. Here's the current page directory that I know that only contains changes from committed transactions. So once my transaction commits and I write all those pages out to disk, I just flip a pointer now in a single record, which I can do atomically, to say, now you're pointing to the new page directory. So this technique is old, but it's very rare. We'll talk a little bit why IBM abandoned this later on. Probably the most famous system that uses this approach is LMDB. Again, he's the opposite of me. He loves mmap. He loves shadow paging. And he's very vocal about this. And we'll see roughly how they do it. But it has some limitations. CalCDB does this as well. They're going to get around the fragmentation problem by only appending the shadow pages to the end of the database file. Of course, you have to do garbage collection to clean that up. FastDB is out of Russia. Gemstone, that's a rando system that's pretty old. And then SQLite did this originally, but they got rid of it. And they switched over to the write-ahead log. We'll see that in a second. Question, where are the shadow pages? Go through the example and you'll see. Yeah, but it's in both. Right. This is also going to look a lot like multi-versioning. But now it's being done at the granularity of a page instead of a single record. Right? And then we talked about taking page locks when we talked about the sort of the hierarchy of locks. And pages were in there, but I didn't really discuss them. You would use page locking for this kind of stuff. All right, so we have our master pointer that's pointing to the master page table. That should be page directory, but it's all the same. But it's basically in memory a mapping through a page ID to some location on disk. So then now when a transaction starts, say T1 comes along and it starts, it's going to create a shadow page table that's going to basically in the beginning just contain the exact same records and pointers to those pages out on disk because there's been no changes made yet. But then as T1 modifies things and modifies data in pages, instead of overwriting the master record database, we're going to instead make a copy of that data first, make a copy of that page on disk or in memory, and then write all our changes to there. And then same thing, as we update other pages, we're going to make more copies of them. Now, any other transaction that comes along that's read-only, right? Well, they're going to always go to the master pointer, which is going to take them to the master page table. So they'll see the master version of the database. They're not going to see any of the changes from the first transaction, right? So LMDB does this. LMDB only allows one writer transaction and can have multiple reader transactions because they're essentially hiding things this way. You don't have to, but it makes things a lot easier. All right, so then now, T1 wants to commit. So what we're going to do is that we're going to make sure that we update the master pointer to now point to the new page directory with all our shadow pages that we've installed. And then once we know that's been flushed and safe out on disk, then now we're essentially flipping the pointer to point to the master page. The old shadow page table comes to the new master page table. Any other transaction that comes along after we've done this switchover will now see the changes that T1 made. And if we crash and come back, we look at the master pointer on disk, and we would know which page directory we should be looking at. So we won't lose any of the changes from this transaction once we said it's committed. And then just like a multi-version, we have to do garbage collection. So eventually, at some point, we got to make sure we throw away the old page table and then clean up any of the invalidated older version pages, right? And then we can just reuse them for future transactions. Yes? Question, does this only allow one writer? In my example here, yes. It doesn't have to. It's just now you got to do the thing he was asking about, like, all right, well, when do I switch my master pointer over? Because I don't want to switch it over with a transaction that hasn't committed yet. So now I got to wait for all the transactions to say, oh, we're going to commit. Then I can do a group commit that way. If you allow multiple writers. If you only allow one writer transaction, then you don't have to do that.
If you always have transactions that hasn't committed, like at any point in time, then
You have to wait. Yes.
you have to go through.
Yes. So that you can get around this a little bit, like if you do page level locks, then your transaction is updating some pages. My transaction is updating other pages. I can't read your writes. That's fine. I go ahead and commit. I update the master pointer to now point to the new master page table, but I make sure it doesn't include any of your changes, and I immediately establish a new shadow page table with all your in-flight changes. You can do it, but it's more work. And then what LMDB does, I'm showing like an example here of like there's a single master pointer, but the data, they're doing index organized storage, so the index is actually the data itself. So in that case, you just change the root of the B plus tree, you swap that to the new pointer, and then that gives you the switch between the master and the shadow. Say it again? The question is this a naive way of doing multi-versioning? So I'll talk about this in a second, but like all these ideas, like between multi-version current control, this logging stuff we're talking about, the shadow paging stuff we're talking about here, we talk about log structured merge trees. All these things kind of are very similar to each other, but oftentimes they're treated as separate concepts because the way you sort of abstract the concerns of the system. So there's a lot of redundancy in this, right? We'll talk about Postgres in a second. Postgres didn't have a write-ahead log because they assumed I would make a copy of the tuple and then write that out, and that was the log. But the performance reasons, right? Then down below that, you have like your file system. That's doing journaling too. That's maintaining its own log as well. And then go even lower than that. Now you got on the actual like SSD. It's doing logging down there too. So it's a lot of redundancy, but like it's just, you know, unless you control the entire stack, which nobody actually can, it's all kind of unavoidable. Except Oracle. But even then, I like they're probably still running on a journaling file system, right? They're still going to do write-ahead logging. They're not a log structure storage system, right? So.
Can you elaborate briefly on, you mentioned shadow paging earlier, 2 lectures back in atomicity.
Yes.
How does this ensure
Atomicity? Yeah. The question is, how does shadow paging ensure atomicity? All right, so going back here. Transaction T1 wants to commit, okay? So it modified 3 pages. So we need to make sure those 3 pages get installed and everyone can see them at the moment we say this thing's been committed, okay? So I can't guarantee that I can do flushing to those 3 pages out on disk atomically, all right? So I need some way to guarantee you through one write, atomic write on disk, that these things have been installed. So that's what the master pointer does. That's a single page, say at the header of the file, and I can guarantee I can write that atomically. So once now I install all the changes for this transaction, those 3 pages in blue, then now to switch it over, I need to do atomic write to the master pointer record. Once that's been installed, then I know now that anybody comes along and reads the master pointer is going to see the shadow page table and would see my 3 changes. So this guarantees that no matter how many pages I modify, that they all get installed atomically, and the single compare and swap, everyone sees them. Okay. So supporting rollbacks is super easy. As I said, if your transaction's in flight and I crash, come back, I ignore what was ever in the shadow pages, right? If a transaction aborts while running, same thing. I throw away the shadow pages for the in-flight transaction that got aborted, and then don't update the pointer, so no one's going to see any of the changes anyway, right? So the problem with this is that copying that page table is expensive. Now LMDB gets away from that, doesn't have this problem because they're copying sort of paths through trees. through a B plus tree, right? But if I have to copy the entire tree, or I have to copy the entire entire page table, then that's expensive, especially for large databases, and this becomes problematic. The other challenge is that, going back here, now I have a bunch of empty space or empty pages in my database file. Now I can maybe get around that by creating a new file every single time, so I don't worry about all these empty pages. But at some point, I got to be able to reclaim them. And in the case of System R, the problem they had when they were running shadow paging is that since sequential I/O is so much faster than random I/O, now I have a bunch of gaps in my tables that I got to jump over and ignore, and that starts to look more like random I/O the more fragmentation I have. So over time, the database would get slower and slower and slower, and then you have to run expensive garbage collection and go clean all that up. And again, in the 1970s, the hardware was like super slow. This became really problematic back then. Yes.
Just curious if that's still a concern in SSD. Like, is there a concept of like being sequential and fast on the
Yeah. So the question is this still concerned on SSDs? Go even faster than SSDs. So we were looking at the Optane stuff from Intel, persistent memory. So it was like DRAM, but it was persistent. So at the speed of DRAM, but like you could ensure your writes were durable. And in that environment, the shadow copying or shadow paging, if I remember correctly, still did not perform as well as like write-ahead logging, because you have to do because you do copy and writes. The copies kill you at that point. So if the disk is slower, the disk writes are that's what kills you. If it gets faster now, the mem copying you're doing in this world gets slower. Now, I don't think this is a few years ago. Optane is dead, of course. You can't buy the hardware, but I still think findings still hold today. But I'd have to go look again. The question: if it was an SSD, do we care about hardware prefetching? What do you mean? Yeah, statement is like I want things to be as sequential as possible, because that's, again, if I'm doing scans, it's going to be faster. And so even the LMDB stuff, because it's a tree structure, things are more scattered. But if you're only doing point queries, maybe not that big of a deal. But anything beyond that, having everything sequential still helps. And again, you say, oh, is it multi-versioning? Isn't that going to have the same kind of fragmentation? Well, no. If I do it the MySQL Oracle way, where I do newest to oldest, and most queries only need the newest data, then the main table itself is going to have the data I want, and I don't have to go look at the Delta records. Yes?
So for the naive approach that's building memory, they talk about when one transaction wants to commit, but the page has some dirty data, make another copy.
Yes.
But you don't need to do that here, right? Because you only switch the pointer until all the transactions.
So the question is, going back here, when I showed sort of the strawman approach, I had to make this copy here for the page because 2 transactions modify the contents of the page. And only one of them is allowed to write things out. So I had to make a copy and make sure that copy didn't include the changes from the first transaction. Assuming I have a single writer under shadow paging, this problem doesn't occur because only one transaction is allowed to modify a page. So it might take a lock on the whole page. So when I write out the disk, I'm only writing out the disk. It's only going to become the master version when the transaction goes and commits. And because I'm doing a single writer, they won't contain changes from uncommitted transactions. So I don't have this problem. If you have multiple writers, then you have to do that reversal thing I said before, right? But if you take page level locks, exclusive locks on pages, then 2 transactions can't write to the same page under the scheme. Okay. So I don't want to dwell too much on shadow paging because, again, nobody does this, or very few systems do it. I do want to show what SQLite used to do. So SQLite did a version of shadow paging called rollback mode up until 2010. Then they got rid of this, and now they use write-ahead log by default. I think you still can switch it back on if you wanted to for like compatibility reasons. It's famously backwards compatible for like the SQLite guarantees that the SQLite file format will be supported until 2035. right? Because again, this thing's running in satellites, it's running in planes, like this is a critical piece of infrastructure. You need to make sure that it runs forever, right? So that's why you're very unlikely. Current version of SQLite is SQLite 3. You're very unlikely to see SQLite 4 anytime soon. All right. So the way it would work is that there wouldn't be a sort of page table. There'd be this separate journal file. And what happened is, anytime I wanted to make a change to a page in memory, but from a transaction. And by the way, SQLite was like LMDB, one writer, multiple readers. So only one writer thread. We don't worry about concurrent updates from different transactions. So before I modify page 2 in memory, I'm going to make a copy of it and flush it out to disk in the special file called the journal file. Right? That was separate from the main database file. Then once that's been flushed, then I go ahead and make my change to page 2 in memory. Same thing, I want to modify page 3, right? I make a copy to the page in the journal file, and I go ahead and then modify page 3. Then when I want to say my transaction is committed, now I'm going to make sure that all of these changes have been written out. So I start writing out page 2 to disk, right? Flush that, that's fine. But then as I start trying to write page 3 during this commit process, there's a system crash, and I lose all my contents on my buffer pool. Right? So again, going back here, in order for me to say the transaction is committed, I got to write page 2 and then write page 3. And once I know that's done, then I can tell the outside world you've committed. But if I crash before then upon recovery, when I come back, the first thing I'm going to go do is look in this journal file and figure out what was in there. Again, these are the copies of the data before I made any changes. So I'm going to go bring in page 2 and page 3 back into memory. And I know that this is to be the current version of these pages before I start running new transactions, right? In order to say I completed the recovery process, I got to make sure that whatever I got from the journal file is what matches what's actually in the database file itself. So I'll go ahead and take page 2 and make sure I just overwrite whatever's in the database file for page 2, and I'll do the same thing for page 3. Since I don't know what's in there, I know I got to just overwrite it to make sure that it's the version I expect. What do you mean if it didn't commit? What didn't commit? Sorry. Right. The question is, what if the transaction that modified page 3 doesn't commit? Well, that's this case here, right? So page 3 isn't written out in the disk. I crash, come back. I don't care what is in this thing. The journal file says this is the page before the transaction started running. So if I have things in my journal file, then I know there's a transaction that didn't commit successfully. So I need to go take whatever's in my journal file and make sure it goes back down into my database file. No. So the journal file is before the change, right? So again, So I'm showing, like, maybe it's hard to read. There's the boxes are blue. So maybe I change to page 2, maybe page 3. Blue boxes, only the blue box page 2 got written. That crashes. So then I bring up the white boxes for page 2 and 3. Yes, I should make that more clear. It looks good in the slides. It doesn't look good in the overhead, or it's clear on the overhead. Not as clear on the overhead. Right. So it's kind of like it's the opposite of the shadow paging, where like the master page would tell me, here's things that there's in my shadow page table, I have changes from uncommitted transactions that I just ignore. The journal file is like, here's the things you need to roll back and undo, because my transaction might have modified these pages and then it didn't commit. You make sure those things get reversed. Yeah, the statement is correct. Yes. So after I replay the journal file, bring that back to memory, write them back out the disk, then I delete the journal file, and then I can start executing new transactions again. So we can give a demo next class, but like if you go read the debug log of pick your favorite database system, it'll say when it first boots up, doing recovery, and it's looking in the log, looking at checkpoints, trying to figure out, or if it's got a journal file, looks in that, trying to figure out what was going on at the time when the last time I was running, because it may have not been a clean shutdown. All right. So as we said before, shadow paging requires us to do a bunch of random IOs to potentially non-contiguous pages on disk. Even the SQLite method, right? Those pages were right next to it, it was 2 and 3, but like they could have been all different parts of the file, and I'm doing a bunch of random IO to write them out. And we said in the beginning of the semester, and we've repeated this many times, sequential I/O is going to be faster than random I/O, even on modern SSDs. And therefore, we want to choose algorithms where we can maximize the amount of sequential I/O that we're doing. And ideally, we want to be able to choose algorithms where we don't have to write entire pages out the disk, even if only a small portion of it, a small portion of that page has been written out in the disk. Right? So CalCB is going to get rid of the random I/O problem because they're just going to append the shadow pages to the end of the file and then truncate it later on and do sort of compaction like a log structure merge tree. But they're still going to have to copy the entire page out the disk, even if only a small portion of it has been written. So the solution to this is going to be the write-ahead log. And as I said, this is pretty much every single data system that supports durable transactions and recovery is going to be doing this approach. So the idea is that we're going to maintain a separate log file on disk or non-volatile storage that's separate from the database file, and that's going to contain all the changes that transactions make to the database while they're running. And we're going to assume that the log itself is going to have enough information for us to allow it to undo and redo any transaction that has come along and either committed or did not commit. And the most important thing you got to understand about the write-ahead log is this paragraph right here. And that is, the database system is not allowed to write out any page that's been modified by a transaction from the buffer pool, cannot write that out to disk before the log record that corresponds to those changes has been safely written out the disk. Right? That's why it's called the write-ahead log, because you're writing ahead to the log before you write to the database system. There is write-behind logging for the experimental hardware that he and I were talking about. And we did that, and you actually want to write to the database first before the log. That's only in research land. Don't do that for real. Right? It has to be before. And so with this allows us to do steal and no force. So steal is going to allow us to write out uncommitted changes, changes from uncommitted transactions before the transaction is committed. But again, we got to make sure we write the log records first before those pages get written to disk. And then no force says that we don't require the database system to flush out all the pages that transaction is modified when the transaction is committed, but we got to write out the log records for that transaction first before we tell the outside world you've committed. So that means that if a transaction modifies 1,000 pages, there'll be 1,000 log records, or at least for those changes, and all those 1,000 log records we got to write to disk. But we can do that sequentially with a fewer number of IOs versus doing random IOs for all those 1,000 pages, as we would have to do in shadow paging and other techniques.
So I think that people can do shadow paging because the buffer pool for policy of no steal and force is easier to implement. Is that what it is?
The question is, are people doing shadow paging because no steal and force is easier to implement? Yes. But it's like you can do it quick and dirty pretty easily. Because the write-ahead log, well, see as we go along, it's a bit more complicated. And then when you throw checkpoints in, that's hard. Because now you got to be able to handle, what if I crash and recover, and then during my recovery, I crash again? That's hard. Shadow paging doesn't have that problem. All right, so again, I'll sort of go through this quickly. But for force and steal, right? If I force, it's trivial to do. But I want to be able to do steal because I want to be able to write out pages before transactions committed, right? So again, this is repeating what I said. Like if you do force on every update, you flush all the pages before they go to disk. If I do no steal, then I can't flush anything out before transactions committed. But it makes it trivial for us to do rollbacks on the aborted transactions because you just throw away everything in memory and nothing's out on disk. If I'm doing no force, then in order for me to cover after a crash, I need to maintain log information to know that transaction is committed and make sure I can redo any of the changes so I don't lose them. And then if I'm doing steal as well, I can flush any dirty pages out the disk, even the transaction is still running, but I need to make sure I can undo those changes later on if I crash and come back. So let me walk through this and then hopefully this make more sense. So again, now we're going to have these log records we're going to maintain for transactions, but now we need a place to store them. So there'll be some area in memory that where we're going to basically append changes to we're going to append the changes to our this memory buffer as transactions make them. It says usually backed by buffer pool. That's usually not the case, right? It's just memory, right? Right, and then again, all the log records for transaction for the pages they modified have to be written to disk, non-volatile storage, before the page itself is allowed to be overwritten. So again, in your buffer pool replacement policy, when you or in the background writer, when you go through and start evicting pages and writing them out to disk, you got to make sure the log records that dirty those pages, those are written to disk. And we'll see how we're going to track that next class using log sequence numbers. You basically keep track of a number that says, here's the log record that corresponded to this change. I know it's been written to disk, therefore I can evict this page. And then we don't tell the outside world that our transaction is fully committed until all its log records have been written to non-volatile storage. Stable storage is the same thing. All right, so the way this is going to work is that when a transaction starts, we're going to put a begin record into the log as represented its starting point. It's kind of not unnecessary for today's class, but next class we'll see it because we need to know when a transaction showed up when we do recovery to figure out where like the demarcation line is the starting point, which is starting point of the transaction. Then anytime that a transaction makes a change to an object, we're going to record a new log record that keep track of its transaction ID, the object ID of what got modified, then the before value for undo and the after value for redo. If we're doing multi-version concurrent control the Postgres way, we don't actually need the undo value because we're never overwriting things. We're always making a new copy of it. But again, to be super careful, we'll record both. Then when a transaction finishes and say that it gets committed successfully, then we're going to append this commit record to the log. And then we need to make sure that all the log records that come before this commit for that transaction get written out to disk before we come back with acknowledgement, say your transaction is successfully committed. Now this means that we may be writing out log records from transactions that have not committed yet, but that's okay because we haven't written the commit record yet for them. So again, when we crash and come back, we see a bunch of changes, a bunch of log records for changes, but then not the commit. We know we need to reverse that, undo that transaction. So it's okay for us to write out changes from transactions in our log records that have not committed yet. All right, so when transaction T1 starts, there's a write on A, right? We append a log record that says our transaction has begun, right? And then now when we do a write, the first thing we got to do is append a log record in the right-hand log buffer that corresponds to the change. So our transaction is T1, we're modifying object A, and then we have the before and after value. And then once that's written, appended to the log, everything's still in memory here, so that's fine. So that's fast. We append that log record, and then we go ahead and make our change to the data object itself. Then we do another write on B, same thing, append the log record, then modify the page. Then when our transaction commits, we put a log record in to say T1 has committed. Then we do an fsync, flush that out to disk, and then once now the hardware comes back or the OS comes back with an acknowledgement saying that our change has been flushed to disk, then we can tell the outside world that our transaction is committed. Yes? The question is, we never put the values in non-volatile storage, in the buffer pool. Yeah, that's the whole point. That's fine. Right? Because everything I need, if there's a crash, everything I need to be able to recover the database, if there's a crash, is in the log. Right? So again, if I get blasted by power outage or whatever, the OS crashes or whatever, right? That's okay because everything I need to replay that transaction is up above in the write-ahead log. And I can bring that in memory upon recovery. Next class we'll talk about how we handle that, and I can just replay the transaction changes. Of course, now, if I have to flush the log for every single transaction in order to say it's committed, right? If the log flush on a fast SSD takes 1 to 5 milliseconds, then that's going to really become a bottleneck in my system, right? Best case scenario, if a log flush takes 1 millisecond, then I can only run 1,000 transactions a second. That's super slow. Like some sites want to run 100,000 transactions a second, or 1 million transactions a second. So the way to get around that is through a simple optimization called group commit, where when a transaction wants to go ahead and commit, then it'll wait until a small timeout period. Right? Think of like every 5 milliseconds, the system will say, if I have any changes from a transaction that wants to commit after this timeout, I'm gonna go ahead and write it all to disk. I'm basically batching together a bunch of changes in my buffer pool, sorry, in my log buffer, and then those things can all get written out together. So I'm not blocked waiting for one commit after another. Say it again. When you say queries, what do you mean? The question is, can a transaction only commit in 5 millisecond intervals? Yes. That's pretty good. Yeah. Because I can commit, whatever, 10,000 transactions in that 5 milliseconds. I would say the general rule of thumb in databases is that anything below 50 milliseconds is good enough. If you get into high frequency trading, those guys do cocaine. They want to be under a millisecond, right? They want to be microsecond level. But most websites, like the 50 milliseconds is the upper bound of what you want to be for a transaction commit time. And this comes from like internet advertising auctions. Like when you go visit a website, assuming you're not using uBlock Origin, then when you visit a website, the Google ads or whatever the ad broker sends bid requests to a bunch of other advertising brokers, and then come back and say, whether they want to, how much they want to pay to show you an ad or something, right? And the timeout request for that is like 50 milliseconds or less, maybe 40 milliseconds. So you basically, you get a request, you need to do some kind of run a transaction and come back with a response within 40 milliseconds. Say it again? Is there overhead? Yeah, there's network overhead. So yeah, so like, but say that the deadline is you got to be back in 50 milliseconds. So say like you get a request, you have 40 milliseconds to figure out what you want to do and send back, right? Or anytime you like update a website, like you want to be back 50 milliseconds is the general rule of thumb. So if I'm committing every 5 milliseconds, that's good enough. That's pretty good. All right, so again, the way it works like this is that now we're going to have 2 log buffers, right? So T1 starts, it begins the transaction. We put our entry in the first log buffer, does a write on A, ends up there. Again, assuming I'm not showing updating the pages in the buffer pool, assume we're doing that too. Then I do a write on B, context switch over to T2. T2 does begin, does a write on C, does a write on D. Before we do the write on D though, our buffer pool is full. So now we can go ahead and asynchronously flush this out the disk. But in the meanwhile, now we just switch over now to using the second log buffer. So we write all our changes there, right? And then say now there's a stall and we go ahead and do a bunch of commit. And at this point here, the first transaction T1 will wait until the timeout to do group commit in the second log buffer. And then when that happens, again, think of like in milliseconds, then we write out the change from the second log buffer out the disk. Right, so basically, I'm showing 2 buffers here. You could have more than 2. I could basically always be writing things out to disk. And they're all sequential writes because I'm just appending to this log file. I'm not doing random IO, so this is pretty efficient and pretty fast to do. Yes?
So what do you do for the HFT guys?
The question is, what do you do for HFT guys? They usually run in-memory databases, and then they can do, they replicate.
Like they just pray they don't all fail.
The question, they pray they don't fail. Yeah, they're also not running on like machines you find behind the dumpster. Like they're running on high-end machines that like they're fault tolerant. Then there's a whole other class of databases called super fault tolerant databases. We're getting ahead of ourselves. But there's a system called nonstop SQL that's basically, it's like NASA level replication. So like you run a transaction and it runs in parallel on 3 machines and they all come back and say, yes, we did the same thing. Like they do that kind of stuff, right? They also, they build their own hardware. Like they'll run fiber under like the Hudson River to get an extra 5 millisecond lower latency from like the data center to like the trading headquarters. They like, they're just minting money. They do whatever, right? All right. But the core idea is basically still the same. All right. So again, as I said before, there's a lot. It seems like a lot of overlap when I'm talking about here. For there's a write-ahead log versus the log structure storage we talked about before, or append only MVCC. And yes, there is a lot of sort of duplicated ideas here. I will say, though, in the case of log structure merge trees, they're still going to have a write-ahead log for the mem table, right? The mem table is like that skip list or B+ tree that's in memory that's absorbing all the writes, and then eventually gets full, and then you compact it into an SS table and write that out to disk. For that mem table piece, since that's not durable, it's in memory, they're going to maintain a write-ahead log for that as well. Then once you know the mem table has been converted to an SS table and written out to disk, you can then truncate the log. So even though log structure storage kind of looks like the same, they're still going to maintain a separate log file as well, doing the same things we're talking about here. All right, so now, again, if we go look at, again, no steal versus steal and no force versus force policies, you can break up the sort of performance characteristics of these two approaches based on what happens when the system is running during normal operations and what happens during recovery. And part of the reason why most systems are going to use no steal and force and with the write-ahead log is that it's going to be the fastest approach to use for during normal operations. If I assume my database is not going to fail every 5 seconds, which, if it does, you have other problems. Like, you assume my system is not going to fail all the time, then the write-ahead log approach is actually going to be faster. And so then you pay the penalty for slow recovery. But again, if I don't think I'm going to crash that often, or if I start replicating things the way that I was briefly mentioning there, then it's less of an issue, right? And the reason why the recovery be faster with force and no steal is that I don't have to do any undo or redo. Like in the shadow paging case, I just come back and I ignore whatever's in the shadow page table, and I'm good to go. My data is consistent. All right, so in my example so far in PowerPoint, I've been showing like, oh, here's T1. I'm showing the log records as here's T1. I'm modifying object A, and then here's a before and after value. But in actual system, we have to be more concrete and understand what we're actually going to store in our logs. And there's basically 3 approaches to do this. One is to do what's called physical logging, where we're storing a byte level diff of the changes we're making to a specific page at a specific offset in that page. Right? Think of like making a diff patch in Git or in Linux. Another approach is to do logical logging, where I store the actual query that made the changes to the database, like the actual little SQL string itself. And then that way, when I crash, I just come back and replay re-execute the SQL query. And then a hybrid approach is sort of physiological, where I don't want to store the actual SQL query itself, but I maybe don't want to store byte level diffs. I want to be able to just keep track of like, here's the pages I modified, and then here's a high level change of what I modified in my page, so that upon recovery, I don't have to make sure the page is exactly the way it was before. The data system can decide to reorganize and move things around within that page itself, and things still work out the same, and I don't lose any data. I'll say also too that what I'm not talking about so far is, we've been assuming we're modifying tuples, but we have other data structures we need to make sure that are safe on disk as well. Indexes, right? Indexes are basically a second copy of data. So in addition to writing out log entries for the data pages themselves, I want to write out log entries for my indexes as well. So upon recovery, I want to restore them. Because otherwise, if I have to rebuild the index, I got to read the whole table all over again and repopulate it. And that's what the in-memory database guys do. If you assume your primary storage database is in memory, like in HFT world, they do this a lot, where you say, I'm not going to pay the penalty for writing log records for the indexes so that I can rebuild them more efficiently when I crash. I'm just going to read since I have to read the whole database anyway and bring it to memory, I'll rebuild the index when I bring it to memory. And then they end up doing less logging. All right, so let's say sample query, select update foo, set value equals XYZ, where ID equals 1. Again, in physical logging, again, it's the low level diff of what's actually in the bytes. So I would say in this page, at this offset, I want to write these values. And again, I still have to have the before and after value because I want to know what was there before. I want to know what I want to install in it. And I would have to do the same thing for the index. In logical logging, I just record the query. To say, hey, there's transaction T1, and here's the update query that it ran. course, now the challenge with this one is, in this case here, it's pretty simple, right? We're setting a value, the value XYZ, setting to an exact value. If I have things in like a random function, time functions, I need to make sure that when I replay the log, that I get the same values for those function calls as I did when I first ran them, because I don't want to run this update query, get today's date and time, then I crash and recover it and replay the same query and get tomorrow's date and time, right? Because then my changes aren't durable, and that's bad, right? But obviously, if I update a billion tuples with my one update query, I only need to put one log record for that update, whereas like physical logging, you got to record a billion log records for them, assuming they're across a billion pages. And then physiological logging, again, it may seem more nuanced, but again, basically think about it as, I got to store what page I'm updating, but now I'm just going to say what slot number I'm modifying, because that's corresponding to a logical tuple within the page. And then the slot can change, where the slot is pointing to in the page can change. And then upon recovery, I can move things around, and I still have the freedom to, I have the freedom to reorganize things, but then still know how to apply the changes correctly. And then same thing for the indexes as well. So logical logging is nice because you end up writing a lot less data for the changes you make to your database. But the challenge is going to be, as I said, you have timestamps and other non-deterministic functions. You make sure they are deterministic upon recovery. And likewise, if I have transactions running at different isolation levels, I need to make sure I replay the log in the same ordering as I did when I actually executed them. So I need to maintain more metadata about the ordering of the actual true ordering of transactions when they actually executed, not the logical ordering necessarily. The other thing about logical logging too is if the query you get logged took an hour to run, there's no magic wand that can make that query run faster upon recovery. So if a query took an hour to run during normal operations, when I crash and come back, it's going to take an hour again to run that same query. So recovery could be potentially slow. So most systems do not do logical logging. Most systems are going to do physiological logging. Yes? The question is, do database systems allow you to choose what you want to do? Not for recovery on the, as the regular mechanism for the system to do recovery. It'll show up when we do replication. So it's actually the next slide, right? If I want to apply changes that I make from one database to another database, so that if this node crashes, I can just pick up where I left off on the other one. Sometimes I can do logical logging. Sometimes I can do physical logging. And those you can change what you want to do. In Postgres at least, other systems less so. All right, so one of the cool things about the write-ahead log is that we can use it for other things other than recovery. And again, basically what I just said to them is that we can use it to propagate the changes on our database to other sources that want to be aware of those changes. So one example would be like if I have I have 2 copies of Postgres, and all my writes go to this one, and I want to make sure that any changes on this one gets propagated to the other one. I can just send them the log messages, the write-ahead log, and to that second database system, and they can pretend that it's in recovery mode and just replay the log as if it was recovering from a crash, but it's just replaying the log that's coming over the network. And this shows up in a lot of times in systems that are doing the ETL stuff that the DBT guys talked about, where I want to run analytical queries or transfer my data in a certain way so I can install it into Snowflake or Databricks, whatever my data warehouse I want to use, and do a bunch of AI analytical stuff on that data. The change data capture technique is basically one way to essentially do that. And so the most efficient way to do this is to do the write-ahead log replication, right? As I'm writing out the write-ahead log to disk, I can also write it out to the network, and then some other node on the other side knows how to process that data and do something with it. So again, like this, I got my write-ahead log, I commit a transaction on this node here, and I can send it over to this other node here. Now we won't talk about how to make sure that these things are consistent. So if one guy crashes, how do we make sure that all our changes are made to the other one? That'll be starting next week. We'll talk about how we handle that. But there's a bunch of tools that know how to interpret the contents of the write-ahead log, because these things are well documented, and then can extract them and do like queries on top of them and transform them in different ways. So the most expensive one of these is probably Oracle Golden Gate. And then the open source tool called Debezium. And you can connect this with like streaming systems like Kafka where you can take the output of a Postgres write-ahead log through Debezium and then convert this into like JSON files or JSON documents that you can then process on, crunch on them, transform them, and then send them off to other systems for consumption. Again, we'll talk about a little bit this more about starting next week. But when we talk about replication, the basic idea is like the write-ahead log doesn't have to be on disk. It could actually be a network stream to another system itself. And all the mechanisms we're talking about here today still work. All right. So now to finish up, the obvious problem with everything we talked about so far, with write-ahead logging, it is the preferred choice, is that it grows forever. Right? My database system has been online for a year. My write-ahead log will contain a year's worth of write-ahead log messages. And so that's going to suck if I crash and come back, I don't have to replay an entire year's worth of log in order to recover the database. Right? Even if I'm doing physiological or physical logging, where reapplying the changes very fast, not rerunning the queries as I would in logical logging, I still got to crunch through a year's worth of log messages, and that's going to take a long time. So the way we're going to get around this problem is through checkpoints. The checkpoint is basically a mechanism where we say we're going to write out all the dirty pages that are in our buffer pool. We're going to write them out the disk, record that as a checkpoint, or apply that, flush them out the disk. And then now we're going to record in a log message that we took a checkpoint at this point in time, so that when we crash and come back or restart the system and need to examine the log, it sort of bounds how far we have to look back, because we would know that there's not going to be changes from transactions that didn't make out the disk. Right? At the moment we take the checkpoint, those dirty pages have been flushed out. So we don't have to look at the beginning of the log. We only have to look back just a little bit to some sort of safe point in time. So I'm going to first talk about how to do this a naive scheme called blocking checkpoints, and then we'll see the problems of this. And then again, as I said, next class we'll pick up with how to make this thing actually usable. Okay, this is basically what you don't want to do, but it'll solve the problems that we want to have and not having to look at the entire log, but it's going to have other problems. All right, so the blocking or consistent checkpoint protocol is pretty straightforward. You basically pause all queries from executing. Right, wherever they're at, you stop. You don't let any new transactions or any new queries start. And then now you're going to flush all the log records that are in your buffer log in memory. You write that out the disk first. Then you can take all the pages in your buffer pool that are dirty and flush those out the disk. Then you write a checkpoint entry to the log, flush that out the disk, and now unpause and resume all query execution. So let's see what it looks like. So say this is our write-ahead log, we're applying a bunch of changes, right? And then at some later point, we're going to crash. You see we have a checkpoint entry in here, right? So when we crash and come back, you basically replay the log going from the newest record to the oldest record. So you go back in time from the bottom to the top. So you start from the bottom, scan up until you find the checkpoint here, and now we know this is the starting point where we want to make sure we apply all the changes that come after this, because anything up above we know has been made out the disk, right? Because those pages have been flushed. So at this point here, we know that any transaction that committed before T1 can be just ignored, and we don't have to do anything because we know their changes are safely on disk. But we're really looking, so in case here we ignore T1. But here we would see that we have T2 and T3 exist, and we could scan up until we find them. But again, if we see a commit, we would scan up and find them. If we see a commit from them, we know we ignore them. In the case here, T2, T3, they made some changes after our checkpoint, so we got to make sure we undo those changes because they didn't commit before we crashed, right? So we need to redo T2 because T2 committed after our checkpoint, and we need to undo T3 because it didn't commit before we crashed. Yes?
Don't you still need to scan the whole log because you need to find all the connections that happen?
The question is, do I need, in my toy example here, do I need to scan the whole log? Because there may be other transactions that made a bunch of changes at the beginning, and I didn't see any more things after my checkpoint. Yes. We'll fix that next class. Yes. All right. So they brought up a good point, but one is One is, again, there may be changes from transactions that have not committed yet, that aren't doing anything. So I still got to scan the log to find them. So next class, we can store some metadata about how to keep track of what are the actual transactions that are running so that we know what we need to go find them, right? The other problem is that in order to make sure we have a consistent snapshot of the database, we have to pause all the queries. And again, depending on how big our buffer pool is and how dirty it is, we may have to write out all the page, write out a lot of pages, and that could take a long time. So now your queries are running, a checkpoint happens, and it blocks all your queries until you flush everything out the disk. So if my buffer pool is like, say, 100 terabytes, again, it's not outlandish on high-end systems, and all the pages in my buffer pool are dirty, in worst case scenario, I got to write out 100 terabytes before any query can start running again. So that's problematic. To the point they said also, well, I got to find all the committed transactions, which take a long time. And then the other challenge is like, how do we decide how often should we be taking these checkpoints? So we have to pause every so often. That's not good. I don't want to take checkpoints too often, but then now my recovery time is going to take longer because I have longer gaps between my checkpoints. So if we spend all our time just flushing out dirty pages from the checkpoints, then that's going to slow down queries. But again, if we don't do that, then that takes the recovery is going to take longer. So there's no right answer. I can tell you how often you should be taking checkpoints. Even if you do the better ones, the fuzzy ones, we'll see next class. It depends on the pain tolerance for whatever your application or whatever your company is. So the HFT guys, they don't want things, they want to recover right away. So they'll take checkpoints every 5 minutes. But for other systems, that's probably more than you need. Now, it can be based on time, or it can be based on, in a lot of systems, it's based on how much log records, how much log record data you've generated. So like say MySQL, it might be like 512 megabytes of log data, then I take a checkpoint. So that way I'm not taking checkpoints at regular intervals. I only do it when I write a bunch of stuff. So if my data system is idle, I'm running video and queries, I'm not taking checkpoints needlessly. So how to do this correctly, again, depends on what your tolerance is, but every single data system will expose different parameters for these things. So again, next class, we'll talk about how we actually make this checkpoint thing for real and handle the case where we can find transactions that were running at the time we took the checkpoint and not have to block anybody while we do it.
So in all protocols, do you always have write-ahead logging implemented? Do you always keep the log since inception of that database?
The question is, if I'm doing write-ahead logging, does that mean I should keep the entire write-ahead log since the inception of the database? No, checkpoints will allow you not to have to do that, the correct checkpoints. There may be external factors that require you to do that. So if you're a financial firm, I got to keep things around for regulatory reasons, like for auditing, like Sarbanes-Oxley. So you got to keep the write-ahead log around for 7 years, right? Because I need to be able to say, what were all the changes that I made, right? But in most systems, you don't need that. And I think Postgres cleans them up. I think MySQL, the old versions didn't clean them up. I think the new versions clean up the log pretty efficiently, right? But in general, yeah, if you don't need it, like if you take checkpoints enough, you don't need I don't need last year's write-ahead log. And then when we talk about fuzzy checkpoints, even if I have last year's write-ahead log, I won't even have to go look at it. It's just there taking up space. All right, so again, the main takeaway from all this is that write-ahead logging is going to be the superior choice in implementing your data system, right, to ensure durable transactions. And the core ideas of write-ahead log is the steal no force policy, where steal means we can write out dirty pages before transactions committed, and no force means that we don't require all those dirty pages in memory to be written on the disk, but we do require all the log records for that transaction to be written out on the disk. Now, the dirty secret is every major data system is going to support what are called synchronous commits to make sure that I flush things to disk before I tell you you're committed. It's not on by default in most systems. Like in Postgres and in MySQL, I don't think it's on by default. So even then, like even though in write-ahead logging, you say your transaction committed, there's still like a 5 millisecond window depending on your group commit interval where you could still crash and lose data. So if you really care about performance, if you really care about not losing data, you make sure that that thing's turned on. All right, so again, next class we'll be taking better checkpoints. So we don't have to block the system. We don't have to scan the entire log. and allows us to do more efficiently. And then we'll show how we actually take our logs and take our checkpoints and do recovery for this. And the algorithm we're going to use is called Aries. And this was invented by IBM in the paper came out in 1992. And although the techniques, I'll describe what the textbook describes as Aries and what the original Aries papers talks about. Most systems are not going to implement exactly as I'm describing here, but the high level ideas of doing redo or analyze, redo, and undo is going to be very similar. Okay? Question, did IBM invent shadow edging? Yes. So if you hang around any of the old school database guys at IBM, you tell them whatever your research is, they'll tell you they invented that in the 80s. So IBM always invented some shit before, right? But then a lot of it they didn't write about, right? At least in this, the paper for Aries, it's amazing. It's 70 pages. It's because it's hard. Because like, how do you make sure you don't lose data? Like that's the gold standard of how you make sure your database is recoverable after crashes using Aries. But a lot of it they didn't publish. Okay, hit it.
Cash money, click, flips, acrobats over tracks. 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 Get the fortune, motherfucker fan. Maintain but never strain flow with the grain. Get the fortune, motherfucker fan. Maintain but never strain flow with the grain.